Yeah.
I'm going to talk about an interesting emerging area called computational imaging. And this actually is highly interdisciplinary topic. Uh, it involves physics, it involves mathematics, algorithms, it involves system engineering, and also if you think about applications, applications are almost everywhere. Okay, and so I will start by giving you some thoughts on what imaging does today. For all of you who are interested maybe in pursuing any area of science and technology, uh, imaging systems are actually everywhere. Okay, so we can go from very small length scales like this 10 raised to minus 10 meters to all the way 10 raised to 20 meters. And we are all familiar with these kind of pictures. So there is a virus at this end. In the middle, I have drawn a head scan as from an MRI system. The virus may be, this kind of model may be generated via an electron microscope or cryo-electron microscope. Galaxy, again, it's a pictorial depiction of that. But the point is, anytime we are trying to understand anything, or any phenomenon or any object, how it works, the best way to understand something is, as we have understood now, is to take a picture of it. Okay, and so even these pictures that I'm showing here, they are possible only because some computational imaging systems or imaging systems exist, which do allow us to even form these mental pictures. And so if you think about role of imaging systems in science and technology today, these are all pervasive, meaning you cannot escape them if you are actually working in any area of science or technology, or you may be working in academia, you may be working in industry, you will always encounter some imaging system that is helping you out in doing work, most likely, meaning I'm not saying 100%, but very large amount of work today relies on our ability to do good imaging. Okay, and so if you are thinking, is this are there is there some sort of a map which tells me where imaging is applied? Meaning I have showed you these length scales, but here I'm getting a little more specific. And these are really vast number of areas. You can take any one of them, meaning I would say that if you go in any direction here, so let's take biomedical imaging, and you can in fact spend whole of your life in that, and still there will be more things to do. And so you have, there is something that at one end of the spectrum is just consumer products like digital cameras and mobile cameras and things like that. At the other end, I have shown more exotic things like quantum imaging that are based on non-classical states of light, some exotic states of light. But then in between, there are many areas where imaging actually plays very important role. So you can think about space-based imaging or remote sensing. There is all these holography kind of displays, and the 3D displays and all that applications are there. Industry, again, for any inspection, non-destructive testing, imaging is very important. The whole of biology or biosciences depends on imaging systems, meaning we won't form a picture of cells in our mind if we did not have microscopes. But beyond microscopes, if you go now into any big-sized hospital, there will be many imaging facilities like ultrasound, CT, X-ray, PET, SPECT, MRI. MRI stands for magnetic resonance imaging. Pathology, for example, all these things, meaning everywhere for diagnostics, it is very important to have access to some imaging system. And, these systems have created kind of a revolution in 20, 30, 40 years, because before this availability of these imaging systems, if somebody is suffering from something, The first step would be, meaning there is no other step other than, to cut open the person, look for, where to operate. But today what has happened is, because of these systems that allow you to make full 3D image of your internal organs, the doctors can, even much before you even go to any operation theater, they already know where to operate, what part to operate. In fact, this idea of interventional surgery now, it actually makes very minimal kind of invasive. It makes a tiny hole in your skin to insert some sort of tools or fibers exactly at the area where the operation needs to be done. And it's really amazing that people can have a whole heart surgery and walk away in the evening, but this is all possible because of imaging systems. Okay. So micro nanotechnology is another whole area where imaging plays important role, because somehow we want to not just see at what is allowed by light, but we can also use other areas, other spectrum like X-rays or things like that, or also non-optical sources like electron sources to make images of structures that are really tiny, nano size, and so that is another meaning. So if you are going to do some science and technology in future, you will definitely encounter one of these areas for whatever, meaning whichever area you try to pursue, some imaging system will always be helping you in that sense. But you see, I have written in the center computational imaging. So what is computational in imaging? Anyway, by the way, is there any questions so far?
Sir, are holograms possible nowadays, or we are working on it?
What are you talking about?
Hologram.
Holograms are possible, yes, no problem.
So would cameras in an artificial space, like those in simulations, would that be counted as imaging?
What do you mean cameras in artificial space? Can you elaborate?
In simulations, for example, in video games, you have three-dimensional spaces and they put a camera inside of those spaces. So would that be counting as imaging?
It will be counted, but let me give you a little more distinction between, what an imaging system like that, what you're talking about, that I would call as more of a traditional imaging. But where is the research themes, or where the technology is headed, that is not exactly that. But let me tell you. Let's go to the next slide. Then this will be clear. Sorry. Yeah, here. So you talked about cameras inside some 3D spaces, but basically the idea is cameras are being used in many applications. Your mobile has a camera, and the pathologist today doesn't just look at the microscope and through the microscope, meaning they also take a picture with a camera. Think about self-driving cars, or your gaming application. So these are more of traditional imaging systems where the hardware is already designed to provide you some image, and then you do some form of processing on the image, or you apply some algorithms to make the pictures better, or find some or make some decisions based on those pictures. Okay, so that I would call as a traditional imaging plus some image processing. And this is already, meaning this is a mature area, I would say, meaning many applications keep coming with availability of processing power. But I think that in all of these applications that I'm showing you, or the camera you put in a gaming environment, physics-wise, nothing new is happening there, because it's just a lens and a camera, and it is electronically transmitting images, and you use them in somehow. Okay, so so there is kind of an assumption that the imaging has already been figured out, and so you actually just use those images to do something, and that also requires, meaning, sophisticated algorithms. So, for example, if you put a camera on a car and is driving, and getting conclusions out of that video about how to maneuver the car, it's not easy at all. Meaning, I'm not saying that it is a low-end problem kind of thing. It is a hard problem too. Where the imaging research as such is going, I would say, is what is shown on the right-hand side, where these are systems which are very interesting because so the first one I will talk about it a little bit later. This is known as planoptic camera. Then the cryo-electron microscopy, or lensless imaging, or super resolution imaging, where you actually beat the diffraction limit. Then the MRI CT, like even the Event Horizon Telescope that you saw. Do you remember seeing these pictures some years ago? Just 2-3 years ago, maybe. This picture came up in the press everywhere. It was a reconstruction of a black hole. So these all are actually computational imaging systems. And why do I call them computational? Is because in these systems actually the image is already recorded on the sensor behind the lens. But here in all these systems, the hardware does not actually provide you with the image at all. It just provides you some data or just numbers, okay? And the algorithms actually are responsible for creating the image itself. So what you record in these systems, if you try to arrange those numbers in any way, they do not look like any images. You cannot make any sense out of it visually. You can make sense out of it visually only after an algorithm has been applied. And meaning this is true of all these things that are shown here. So this black hole, there was no telescope that was directly forming an image there. Okay, so it was some data was collected from antennas across the Earth, and then this data was processed, and then you can actually you have to solve what is known as an inverse problem, or from the data to actually generate an image. And this is where a lot of new activities are happening, because there are many exciting possibilities that I will also show that depend on some very interesting maths ideas. So I will try to explain these maths ideas in a simple way, that why this is important and why these systems are becoming more and more important. Meaning what I see is if you go ahead 10, 20, 30 years, then these things, the camera, microscope, they may not look like what we are used to today. This computational imaging, if it takes over, meaning the microscope could look something completely different. You may not even recognize it as a microscope, but it will do the imaging that you want. Okay. So let us, before I go into anything, let's just, have any of you opened a cell phone to see how the camera looks like inside?
Yes, sir.
Yeah, so there is a tiny box there, and there is a lens that moves up and down with a piezo sensor, and there is a small chip there that that records images. So how does this, even the simple system that you use every day, how does it work? Basically, it's the same physics as I told you, that there is a scene here, there's a lens, this is tiny lens in front of the, at the front end of the camera, and actually see when people claim colors, they are actually not imaging. There is actually a filter of RGB on top of the sensor there. And these sensors, I'll tell you what they do, but you record something, the light on this, and then you can process that and maybe then display it. Okay. But what happens at every pixel is something like this, that you have an incident light that is forming an image, and that generates photoelectrons. You must be studying photoelectric effect somewhere, and so these electrons are actually stored in these pixels. And once when you take an exposure, these electrons are stored in the pixels, and then they are read out sequentially or parallelly. So if it's a CCD type detector, they are actually read out sequentially. If it's a CMOS kind of technology, then these are read out in parallel. But the idea is, once you take an exposure, every pixel collects some photoelectrons. They are trapped there by some potential well. And these trapped electrons, when you read out some charge from every pixel. And that charge that you read out is proportional to the light intensity that was falling onto that pixel. These pixels are, by the way, really tiny, meaning if you go to your cell phone, these pixels are just about 2 microns in size today. Okay, and so you collect some light, meaning the light collected in them is not very large. Even if you are going in ambient, meaning the ambient light in the daylight, still, if you take an area which is 2 micron by 2 micron, it's a very tiny area to collect light actually. And so these electrons are then transferred, and then you read out. So this image that you display on your screen or projector or whatever, what it does is actually assigning some intensity to every pixel when you display. Okay. And so these filters, RGB. Do you know why there are more greens here? Do you see any reason why there are more greens than red and blue on the filter? So these filters are really, this is just a pixel array, and on those there are color filters to do color imaging. So mainly the reason why green is more is because the eye response is more stronger in green, and so it is preferable to have more greens. And red and blue are essentially interpolated. Green is also interpolated at the locations of red and blue. But basically, when people talk about pixels, you have to be cautious how many pixels are really there. Okay. And then we talked about this computational imaging, and so how do we think about all these systems that are very interesting? Because the way to think about this is that you think about imaging itself as some sort of information transfer from the object to your system. Okay, and this object could be anything that you're looking at. It may be self-luminous, or if it is not self-luminous, then you are illuminating with some light. And the point is, when you scatter light from any object, the information about that object is actually coded onto those scattered waves. So there are a lot of things that happen to these scattered waves. If you look at them, they have different at different locations. The scattered waves may have different amplitude, different phase, different polarization, different spectrum, all kinds of things, physical properties actually code this information. And so this information is actually entering your imaging device through some aperture, and this is detected somewhere on a sensor. Okay, so if you think about a camera, why is the lens there actually? What do you think is the purpose of the lens? It actually does, it takes in these scattered waves and applies some phase transformation to these waves so that an image can be formed. But think about a camera or even an eye where the lens is not there. That information in those scattered waves is actually still entering that system. Okay, and so the point is with the computational imaging, we want to think that can I actually detect this information in some unusual way, and then after that you solve a large-scale problem to make an image that is suitable for actually human consumption. And so there are two parts to this kind of computational imaging kind of work. The first is, we want to design, implement somewhat smart hardware for that applies some appropriate transform to these scattered waves. And then once that is detected here, these waves are detected, then you also need efficient algorithms that will actually form image. And now why are we going in this direction? Meaning, why not directly think about a lens that forms an image? The point is that, see, I showed you all these applications where imaging is important, and all these new systems that are coming up. But if you think about, if you ask any person working in these areas or using these instruments, that what is it that they would like 10 years from now? Actually, the answers are generally very similar. They all will generally say that, I want more resolution. I want imaging to be done faster with maybe it should be more noise tolerant, and I should also get more information, because the whole exercise is about getting information. So every pixel in your camera today gives you intensity information, but I would also like other forms of information. Maybe I would like spectrum as well. I would like polarization information as well. And so when you think about gathering more and more information, it appears that just going brute force. For example, if I wanted a spectrum at every pixel, in addition to just the intensity that I'm recording, if you think about putting a spectrometer in front of every pixel, then that's not a smart thing to do. Meaning it's not just hard engineering wise, but it's also not viable. Actually, you cannot actually afford to do things like that. And this afford is actually very important, because when you do science or develop applications, the economics of it is also very important. Unless it is done in a way that meaning it is affordable, nobody is going to use it. Okay. So let us let's go back to your camera and just pose a simple maths problem that so why does this model kind of help us? And so we want to get down to some very basic ideas. Okay. So so I'm going to ask you, how much data is exchanged when you share pictures. You must be taking pictures on mobile and sending it to somebody else. And so if we think about your camera as having nominally, say, 5 megapixels in 3 colors, then if you think how much memory is required to store those many numbers, it is 3 colors times 5 megapixels, which is 15 MB of data. But do you think when you take a picture and send it out to somebody, you're transferring that much information?
No.
How much do you transfer? Why is that so? Where does that information go away? But at the other end, hello.
We share data in about 4 and 500 kbs.
Yeah, so but you already, all of you have mobile phones which have megapixels, right? How come that is so? Have you ever thought about it? So the point is, these pictures, they. So how is it possible that you think about it? It is 15 MB of data, but when you send it, it is just a few hundred KB. Meaning, see, if you had to. Yes.
The compression algorithms and the like, right?
Yes. So the point is, why is that so? Why is this? Has this become so easy? Is because of an interesting way to represent signals. Okay. So the point is, when a picture has some meaningful structure in it and not just random noise, actually the number of numbers required to store it is actually much less than the number of pixels in it, and that is why you can actually send it. If you had to take a picture and send it over your mobile, and just for every picture it took 15 MB of data, then that will be too much. But why all of these things are possible, even in music, why MP3 is possible, it's mainly because the signals that we are considering there, they all have some structure to them. And so the number of numbers, you can always find a mathematical representation of these signals such that the number of numbers that are required to store these pictures is much less than the number of pixels in it. So in fact, this idea is known as sparsity of images. So in the pixel domain, if you take this picture of IIT Delhi building, maybe there are m pixels and every pixel is non-zero. But there is always a representation. But you see that this image has a structure. There is a sky here where the pixels are not changing much actually across this region. And so there are some pixel-to-pixel correlations. And if you can exploit these things, the idea is that you can actually save such signals which have some meaningful structure to them with much less numbers. So in fact, it is much less than even 10% of the number of pixels actually. And this is a very interesting finding which has led to all of us exchanging pictures and signals and in whatnot forms. Okay. But the question for imaging systems is interesting because if you what you are imaging, if it is it is mathematically representable in number of numbers that are much less than pixels, then that poses very important questions for the imaging system itself. So the question is, if we implicitly assume that, or implicitly what you are imaging as an interesting object, if it's the information is actually much less than m, then actually the question is, can we generate the same picture by less measurements? So what do I mean by that? So if we go back to the camera that I showed in the beginning, if I wanted n pixel image, I actually measured n times, because there are n pixels here that form the image, and then the same number of pixels were there as the number of pixels in the image. So the same number of measurements were done as number of pixels. But that's not a very smart idea, because I just showed you that mostly the interesting things, interesting images that have some structure to them, there, the information implicitly is actually much less. And so if we can acquire these images with much less measurements, then